Welcome back to the course on superconductivity. Today we're going to talk about peak displacement, stress, and strain. We'll first go over the orientations of stress and strain in solenoid and then see the generalized Hooke's law. Then we'll define the peak displacement stress and strain. First of all, in a solenoid, usually the cylindrical coordinates are used because of the symmetry and rotation showed by the line in black. There are three directions for stress and strain in a solenoid. The first ones are the hoop stress and strain. They are in the winding direction, so they follow the yellow circle here. The seconds are the radial stress and strain. They are perpendicular to the symmetry axis and follow the red arrow. The last ones are the axial stress and strain that are parallel to the axis of symmetry. Using this system, we can define an infinitesimally small element in 2D on the plane formed by the hoop and radial direction. The element is defined by r1 the inner radius, r2 the outer radius, and its length in the hoop direction r1 theta. If we consider that the solenoid expanded due to the magnetic stress, we can define UR the displacement that defines the difference between the original position of the element with its final position. The radial strain is then defined as the ratio between the deformation to the original size. We can do the same for the hoop strain. Using this element, we can also solve the displacement for the Lorentz force-induced stress, also called BJR stress, in the plane stress case. Considering a magnet that produces a magnetic field B1 at its innermost turn and B2 at its outermost turn with a current density constant over the plane. We can make this equation based on forces equilibrium, the first term being the accumulation of the force felt by each inner element on the element studied, the radial stress, the hoop stress, and the BJR stress. Here we consider that the field changes linearly with the radial distance and define the function as this one. Using some parameter, we can use the dimensionless variable rho that is defined by this ratio, and also kappa, which is the ratio of the inner and outermost fields. Using the functions we defined, and the dimensionless parameters, we get the governing equation with the stress as a variable. We can define the stress in terms of strain using the equations from chapter 3.2.2 for 2D thermal stress. Now using the definition of the strain in this situation, we can change the strains into the displacement variable. Replacing the stress inside the governing equation with the previously defined equation, we get the governing equation in terms of the displacement. For 3D relations, the generalized Hooke's law is used. It links the stress and strain of each direction, accounting also for the Poisson's effect. Usually, to calculate the peak displacement stress and strain, there is 4 steps. The first being defining the governing equation in function of the displacement. Here as an example, the BJR stress, Lorentz force-induced stress, is considered. The second, solving the governing equation. The third, to calculate the strain from the previous results, and last, calculate the stress by using the generalized Hooke's law. After the calculation, we can check if the peak stress or strain would cause significant degradation to the superconducting wires or tapes. On the left-hand side, a figure showing the degradation of the critical current of YBCO tapes versus the tensile strain for 3 manufacturers. On the right-hand side, a picture the little big coil tapes that got damaged during operation. A special case is the NB3 tin wires that when deformed of a certain amount get an increase in critical current. This phenomenon happens until a strain of about 0.35% where the critical current start decreasing as the strain increases as usual. To conclude, by definition, the peak displacement is defined by the maximum strain that is applied to a superconducting magnet while operating. If no precautions are taken, the magnet may reach excessive strain values that will degrade the superconducting wire's properties. NB3SN is a special case where designer will try to get a peak strain of about 0.35% due to the increase of JC at this value.